So far in chapter 10, we looked at two populations and then random samples taken from those two populations. And we looked at hypotheses about whether the two population means are same or different. Then we looked at several scenarios for that, and then we looked at population proportion for two populations, and then we looked at population variance for those two populations. Okay, so now we're going to move beyond just two populations and consider three or more populations. And here we're going to look at, first thing is whether the means of all those different populations are the same, or whether at least one mu is different from the rest. So that's the logical opposite of all of them being the same. So remember, the alternative hypothesis and the null hypothesis must be the exact opposite of one another. So if the null hypothesis is that all the means are the same, the alternative is that the alternative is not that all of them are different. At least one is different from the rest is the exact opposite of that. And this procedure, the testing procedure, is called ANOVA. And the reason for that is ANOVA is a short form of analysis of variance. The AN stands for analysis, O for off, and VA is for variance. So this is analysis of variance. You might wonder, why is it called analysis of variance if we are testing whether the means are equal? So shouldn't it be called analysis of means? Well, not quite, because what we're going to do to test those two hypotheses, whether all the means are same or at least one is different, is by looking at the variance of the condition when all the means are same, and the variance if the condition is at least one mean is different. So we'll compare the variances under those two hypothesized conditions, and based on the analysis of those variances, we'll make a conclusion about the hypothesis about the means. And that is the reason why this is called analysis of variance. We're going to analyze the variance under those two conditions, and based on our analysis, we will make a conclusion about the hypothesis of the means, and for that reason, this is called ANOVA. And here, we need to familiarize ourselves with some terminologies. Okay. Now, when we have several populations and we are checking whether the means of those several populations are all the same, now it doesn't make any sense if those populations means are completely different. You're not going to test whether the GPA of college graduates is the same as production per day in Volkswagen plant. They're completely different concepts. So why you wouldn't do that? So what you would do is you would consider the same measurement for different populations. So if you take GPA as an example, then you want to test whether the average GPA of, say, management majors, marketing majors, HRM majors, finance majors, accounting majors, are they all the same, or is at least one different? So the concept being tested is going to be common, and you're going to use the same concept, either that is GPA or salary or productivity, for different groups, and the groups are the populations. So given this background, let's look at some terminologies. Okay. Here the term factor refers to the groups. Yeah. And here, in the case of GPA example, the factor is the major. What major are we talking about? And that factor has several levels. So it has, the factor is major, and we have marketing major, management, HRM, finance, accounting. So there are five. If these are the five, then they have 5 levels of that factor. So you have factor and then factor levels. The factor levels are also called treatment. So factor and treatment levels. Okay. Now what are we measuring from each of them? The GPA. So GPA is what is called the response variable. So you have response variable, which is the measurement that you take. If you take the sample, and sample will be GPA, GPA, GPA. So what the numbers in the sample stand for, that's your response variable. And you're collecting those response variable values from different groups, and the groups are the treatment levels, and collectively all those groups stand for what is the overriding concept that divides them into different groups, and that's your factor. So factor here is major, and we have treatment levels which are different majors, and then we have response variable, which is the values that you observe. And then we have another concept called experimental unit. The experimental unit is the subject from whom the observation is made. In the case of GPA example, it will be students. Students are the ones from whom, what is the GPA of this student? Who is a management major? What is the GPA of this student in the sample who is a finance major? So the measurement is made from the student, and the students are the experimental units. Okay. So given these concepts, then how are the experimental units selected in the sample? That determines whether the study that we are undertaking is an experimental study or just an observational study. And this is a very critical point here. Observational study is one where the experimental units are self-selected. You have no role in assigning the experimental units to the different samples. So if you take the GPA example, students are already in those majors. You don't get to randomly select a bunch of students and then say, this group is going to be management majors, this group is going to be finance majors. You don't have any say in that. The students self-select, and then you simply observe. So that is an observational study. As opposed to a situation, let's say in a production environment, where you want to try 3 different production methods, and you want to see whether the average productivity among those 3 different production methods are the same or are they different. Now you have the ability to select a random sample of workers and then say, okay, these workers will be assigned production method 1. Okay, these workers will be assigned production method 2, and so on. So when you randomly select and assign experimental units to different treatment factors, treatment levels, and when you make that choice, when you make that assignment, then you are actively setting up the experiment. So this is called experimental design or completely random design. So this is completely randomized experiment. So the difference between these two, as far as the computations are concerned, they are exactly same. Once you make the assignments, and then you make the observations, you have the sample data, then the computations are exactly the same. But the conclusions we derive are much stronger if it is an experimental design, because you have made sure that the differences in the experimental units are randomized. So they are equally distributed among the different treatment levels. And therefore the conclusions you derive are much stronger. You can even go to the extent of saying that the conclusions can be causal conclusions. Okay. There is a causal relationship that you can establish, as opposed to an observational study where you did not have any control over the experimental units getting assigned to the different treatment levels. So then it is less powerful. The conclusions are less powerful, because when self-selecting, students may self-select into management major or finance major, and there may be some other differences among the students' skill levels that may not get evenly distributed as it would in a randomly designed experiment. And therefore, in an observational study, the conclusions that are derived are less powerful. So completely randomized design is where the experimental units are assigned randomly to the groups meaning the treatment factors. Yeah. Now, only one factor or one independent variable with two or more levels. So, see here the independent variable is your factor or the treat, and within that independent variable you have several treatment factor levels. Okay. Now, with this introduction, so let's now look at how the testing itself is done.